Okay, then I propose to start. So, hello everybody. So thanks for joining this this second webinar. I am Mathieu Effelet from Maison de la Simulation, and I will discuss today some progress and some activities we had on FPGA programming. So. Good. So they outlined the following. So I will discuss first the code, the scientific application we are working on and that we use as a use case for porting to FPGA. So first, some optimization and some work we've done on the Fortran version, and then a general introduction on the kind of constraints and how FPGA is working. So Metal Wars is a scientific application. So that's about classical molecular dynamics. So initially developed by Paul Madden in Oxford, and now maintained by Mathieu Salan at UPMC, so Université Pierre et Marie Curie. The original version was a pure MPI code Fortran with some particularities. So it's able to make simulation with constant potential electrodes and polarization effects. So polarization is not used that much currently, but so constant potential electrode allows to simulate the kind of system you're seeing right now. So it's systems that are supercapacitors. So the idea is that's an energy storage device. The idea is the following: is that you have ionic liquid, so that the red and the green balls, as you can see, that's a liquid in which we have we put two electrodes, so that's carbons, so that the blue structure that you have on the left and the right, on which you apply a potential and a difference of potential between the two. Then all the ions will migrate inside the liquid and will be absorbed at the electrode, and so that's how you put energy inside the supercapacitors. And when you want to release the energy, you just have to plug the electrodes to the circuit you want to put energy in, and then the process goes the other way around. So then the problem with this kind of technological device is that it's very hard to measure what happens at the interface between the liquid and the electrodes. That's why they are studying this with numerical simulation. Right. So so the complexity here is that we want to keep a constant potential of the electrode, whereas that's the particularities of this code. In general, in molecular dynamics, we are working with constant charge. So you fix charge once, and then it doesn't move for the whole simulation. Here, the charge on the electrode are evolving as we are putting energy into the system, but we still want to keep a constant potential. So that's where we have we have a minimization process that determines the charge on each atom of the electrode such that the total energy of the system is minimized. So we are using a conjugate gradient for this. So I don't go into the detail of the model. So what we're interested in, so at least my job on the code is to make it faster, and then we are working at the algorithm level. So in total, the code base is about 20,000 lines code, and the really intensive part that really require HPC is pretty small. That's about 7,000 lines. So that's pretty small for a production application, but still, that's really doing science. So we are not working here with a toy code. It's really doing science. So as you can see, inside this time loop, so we have several steps, and so the CG, so it stands for conjugate gradient. So that's where this minimization occurs, so where we have determined the charge on the different atoms of the electrodes. Once we have the charges on the electrode, we are able to compute the force on each atoms of the liquid. Then we can push the atoms inside the liquid, and then with rattle and shake, we form again the different molecules. There are constraints between some atoms, they are forming molecules, and then that's basically one time step of the algorithm. So I don't want to go into the detail, but shortly we've worked on the Fortran version of the code in order to reduce the memory footprint. So basically, we, instead of storing some values and reusing from the memory, we recompute these values when we need them. So that reduces the memory footprint, and as computation are much not that expensive on current architecture, that makes the code faster. We improved the vectorization and introduced some cache blocking techniques in order to reduce the pressure on the memory bus. Overall, we managed to get an acceleration of 3.5 on the CPU version, and we introduced OpenMP and OpenACC to be efficient on the Kernel architecture and to be able to run on GPU. So something important to be mentioned is that I try to keep in mind software maintenance, and we managed to run this code on 3 architectures, so CPU, KNL, and GPU, and by keeping a single code base. Okay, so now we have pragmas inside the code, of course. But we have kept almost a single code base, only a couple of 100, I think, between 100 and 200 code lines have forks. So we have specific version for GPU. So that's quite important, and in the end, we get pretty interesting performance results. So this code is quite intensively used on the supercomputing architecture. So as you can see, there is 28 million CPU hours that have been used recently, and without the optimization that have been done, that would have the kind of work that has been performed would have required 70 million CPU core hours. Okay, so that's so this kind of optimization work allows to better use current infrastructure in order to do more science. And yes, if you think that 1 core hour is between 1 and 5 cents, that's yes, the saving with the saving you could have bought quite a nice car, I guess. Good. So then, as the code is running on several architectures, then we can compare them. So we've run on the Kernel system, so that's 68 cores chip that forms 1 node. So that's on CNES, on the PCP system at CNES. We could also run on the Broadwell architecture, also at CNES. So that's B socket, so with 14 cores on each socket, so 28 cores a node, and also on an open power system that is at Idris. So where we have 1 node is 2 power 8 processor, and for each processor we have 2 GPUs. So that's 4 GPUs per node. So, and in a nutshell, so what I've done is we've pushed the code at its scalability limit. So meaning that we have to reach, we increase the number of resources up until we reach not less than 75% of parallel efficiency. So on Broadwell, typically it happens with 10 nodes, and let's imagine that we are able to do 100 time step of simulation. On GPU, then we have this scalability limit is reached with only a single node. Okay, And with a single node, then we are able to do 84 time steps. And on Kernel, with 5 nodes, we are able to do 62 time steps. So from recitation time point of view, at scalability limits, Broadwell architecture is still the more efficient, the most efficient. But if we look at the energy, from the energy point of view, GPU is the most efficient. So with 1 node, and we are able to, if it requires 1 unit of energy, the same on the Kernel architecture, we require 2.5 more energy to do the same physics. Okay, so GPU is definitely here of a better candidate for energy saving for this code, at least. Unfortunately, the measurements were not precise enough on Broadwell, so I don't have energy results on Broadwell. But I guess it's we can imagine that it's more demanding than the Kernel architecture. Okay, I think we are done for the Fortran version of the code. So the topic of today is about FPGA. But so then, and why are we looking at FPGA? It's when you look a bit into the future, then we already see right now that the budget for the energy budget for a supercomputing system is already fixed around 20 megawatts. And the transistor budget will be soon fixed when Moore's law will saturate. So we don't know exactly when it will saturate, but it will saturate. So the only question is when. And then, so these are bad news for the silicon industry and for machine vendors, but for scientific application, this opens very nice perspective where architectures can be very different. So then the question is, how do you organize the transistor within the chip? So which architecture for doing scientific computation? And then once you have this chip, so which programming model, and then what kind of ecosystem can you build around this new architecture? So FPGA is still very exotic nowadays for doing scientific computation, but okay, why not? Let's have a look at this thing. So currently, FPGAs are used in typically the kind of device you're seeing here. So on the kind of boxes you have under your TV. So the idea that you have the compressed video stream that comes from the internet that goes inside the chip. The chip implements in hardware the decompression algorithm, and then the decompressed video flux then gets out of the chip and go to your TV. Okay. The idea of FPGA computing is to have algorithm inside the chip that are so scientific algorithm instead of this video decompression algorithm. So that's what Maxeler. That's the point. That's what Maxeler, a British company, is implementing and selling. So that's a computing solution that is based on FPGA, and they are selling so the hardware plus software environments that allows to program this kind of chip. So let's compare some figures between the different architectures. So you have standard CPU. So current CPU with the Skylake architecture from Intel. We have the Kernel, so also from Intel. We have the GPU Pascal from NVIDIA, and then you have one new guys here. So this Xilinx chip. So as you can see, all of them are in similar silicon technology. So with 16 nanometers. they are operating at very different frequency and have therefore very different power requirements. So that's the big advantage of FPGA here compared to other architecture of processors. Is that so the envelope of a single FPGA can be is below 50 watts, and whereas so the peak performance, even if peak performance for FPGA doesn't make that much sense, but it's in the same kind of range as processors. So as you can see, so the frequency is not fixed. It's really something that is part of the design of your application, and it influences then the peak performance and the energy budget. And from memory point of view, as you can see, that we have similar numbers. So no big difference here. So yes, so that's, I think, so this kind of hardware device are interesting, at least. So that's the idea we want to follow, is to see also how far we can go with scientific workloads on this kind of chip, because there is a potential of having similar performance for 10 times less energy, and that's would be for when we are talking about exascale computing, where energy is really a crucial challenge. So this kind of hardware can definitely help there. So what is a FPGA? So let's compare this to processors. So on the left you have a sketch of what a processor is. So you have some internal memory, so caches. Then we have several cores typically on current architecture. Each core has some private cache as well. And then processor executes an at the end of the day. So what processors are doing, they are executing a sequence of instructions, okay? And some of them are so doing floating operation, and so these are done in vector processing units. So VPU here stands for vector processing units, and yes, and then you have several of these core on a single processor. Okay, so the big difference between a processor and FPGA is that so processor you have instruction. On FPGA you don't have any more instructions. Okay, and data movement on processor are triggered by instruction. So at some point you will need the value of some array in the memory. You will want to make a floating operation with this value, and so you will have a load instruction that will be executed inside the core. So if this value is already in the register, then the instruction can be executed, and then the floating point operation then will be performed. But if it's not, then it will fetch and then move this data, so from caches, so either inside the processor if it's available there, or from memory if it's not available in the cache. Okay, so in a processor, data movement are triggered by instructions. Whereas on an FPGA, we have very different architecture. So as I said, no instruction anymore. So we have DSP, so digital signal processing units. So they are in purple here. So that's that means that the kind of similar to vector processing unit. The thing is that it's much more versatile. So here you can make floating point operation, fixed point operation, integer with various precision. So that's a very versatile piece of hardware. You have BRAMs. So BRAMs are little pieces of memory where you can store you can store data. You have LUTs, so lookup tables that implement some logic when you need some logic, and flip-flops. That's a device that a piece of hardware, a piece of silicon that is able to store 1 bit of information. So you can aggregate these bits to form register typically, and doing logic with lookup tables. So here it's a bit misleading because you have 1,000 more. So you have a couple of thousand of DSPs and VRAMs on a single chip currently, but you have millions of flip-flop and LUTs. Okay. And so what you program in a FPGA is the way the data are moving. Okay, so you have some data that will come from memory will be stored in a VRAM. Then from this VRAM we will fill some register in a flip-flop. And then this register will be then sent to a DSP to make a first operation, and then the second one, and so on. So what you program, the developer has to do is to connect these elements on the silicon, and in order to implement the algorithm. Okay. So in the end, the data are moving, so are flowing, so through the chip, and then what goes out of the chip is the results of the algorithm. Good. So that's what Maxeler has implemented, what they call data flow engine. Okay, so and how it is implemented. So we have the FPGA. So this Xilinx chip is sitting on a board attached to some DRAM. So typically a couple of tens of DRAM. So I think it's 48 gigabytes that is available. And this board is connected with PCI Express. Then they aggregate 8 of these DFEs on a node. Okay, so connected with PCI Express, and then the node is connected with high performance network, so InfiniBand typically, to have this Maxeler, so accelerator node. And then with these nodes, then you pack them in racks. In the same way you pack nodes of CPU or GPU connected with InfiniBand, and but of course these are accelerators, so you need still a CPU to trigger some computation. That's why you need a CPU, and here that's the CPU nodes are dual socket AMD EPIC in their computing solution. Okay. That's where it's and their way of thinking is that the current software stack and the current architectures, so both on the hardware up to the application, is very complicated. So you have really the application that discuss and go through different layers of software in order to get executed at the very end on the device. And the idea is to still keep this kind of complex application on the CPU, but the really critical performance components are directly implemented in FPGA. So you implement, as they say, so directly the problem to one solution that is implemented in hardware on the FPGA. So you really shortcut all this pile of interfaces. So there is a price to pay, of course, you will see. So of course the computing infrastructure is more expensive than the current CPU or GPU infrastructure. So I don't have details here, but this might change also in the future. Of course, the critical component has to be completely rewritten and redesigned, and rewritten in another language, and also dead code or not useful code is really not allowed here, because if you have a non-useful code in a Fortran application, the binary will be a bit larger, okay, than it could be, but you don't care, because that will be instruction that will not be executed by the CPU. Here on FPGA, if you have some part of your design that will be implemented on the FPGA and is not used, it's devices, part of the device, so piece of silicon that will not be used for your computation. So here you lose a lot when you have that code. So that's the problem, that it's very efficient potentially, but very specific to one single problem. And if the problem changes a little bit, then the design has to be changed a little bit as well. So how do you develop this kind of critical component? So one good thing is that on an FPGA, you know the state of the chip at each clock tick. Okay, so you know exactly how many clock ticks will be required to execute your algorithm. And as it is very simple, then just a spreadsheet is enough to then infer and to have a model of the performance of your algorithm. So all the design is done by just playing around with spreadsheet, putting numbers and so on to make design choices, and then you start the implementation. Then you start writing kernels. So we'll have an example. So don't be scared. There is 77 slides, but there is an animation. So where I will explain how this is executed. So these kernels are then you write kernels in a new language. So that's called Maxeler. Basically, that's an embedded DSL for FPGA programming that is based on Java. There is a nice Eclipse plugin that speeds up the development and allows you to run unit tests on the kernels that you want to develop. And then these kernels, at the end of the day, are called from C, C++, or Fortran with an offload mechanism with data transfer. So that's very similar in that sense to current GPU computing. So one big thing that once you have your application that is completely developed, you need 24 to 48 hours to make a compilation. Okay, so that's really large. So there is no way you will make a trial errors of compile and to see if your algorithm is correct. So it's just too much. So that's why there is a simulator, or at least a hardware emulator, in which you can execute you can see if your algorithm are well implemented and give the correct results. That's how you develop the algorithm, and then it's only when you are sure that it's correct, then you launch compilation, and then you will execute it on the real hardware at that moment. Right. So let's have a look at a simple example. So not hello world, but still a little bit a bit more complex, just to illustrate how you can think of this FPGA computing. So that's one part of the conjugate gradient algorithm. So CGPOT is the potential that we want to compute. Okay, that's the output of our algorithm. So we are working in 3D, and we are working here in Fourier space. So we have 3D of 3 loops that spans in the different modes in the 3 different directions. Okay, and for each mode we are doing 2 things. So we will aggregate some values into a quantity. So that's quantity Q. So, and we are interested in the integral of this quantity. So first we compute K. Okay, that's a value. So here computation are nonsense, okay? But the kernel structure is still relevant for compared to what is done in metal walls. So we have something that depends on the mode you are considering, okay? And for all the atoms of our system, so melt is for the ionic liquid, walls is for the electrodes, we compute some things, okay, times, so d of a, so that's, so for example, the position or whatever, something that depends on the atom you are considering. And so you sum up this, this quantity here, and then you have a second loop that use this integral and multiply it by a quantity that depends on the only for the atom of the wall, okay? And this is aggregated into our solution. And so for each mode, okay, you aggregate contribution of this kind. Okay, how do you implement this on a FPGA? So but before that, let's introduce the players here. So we will consider three modes, okay, only. And we will have three atoms for the wall, and 3, 6, 9 atoms for the melt. So this will be atoms that will be the D quantity for all our atoms, and then they will flow inside our kernel. So that's how it looks like. So the boundary here are the boundary of the FPGA, and inside my FPGA, then I will implement 3 different kernels. So the first one are this will be simple counters that will generate stream. Okay, so that will be the 3 loops in L, M, and N. We'll compute L plus M plus N and take the cosine of it. And in order to get the value of K, this will be the output of this kernel. And this output, it will be an input for my second kernel that has K on one side and the D on the other side, and then make the product of the two and aggregate the value inside this kernel. Once the kernel is finished, then we have our quantity integral of Q. So that the output of this kernel will be an input of this one. And again, we will stream D from memory again in order to make the product again, and then aggregate the results in the CG pot, so the results of my algorithm. And what will go out of the chip will be the results of the algorithm. Okay. So we know in advance the number of ticks that are required to run this kernel. So we will have NB modes here, clock ticks to finish the execution of this one. We will have NB mode multiplied by the number of atoms here, and so the total number of atoms. And on the last one, this one will be the number of mode multiplied only by the number of atoms of the wall. So let's have a look at how it looks like. So we start with the first mode, okay? So we have L equals 0, M minus 1, N equals 0. We do a first addition of L and N, and then while we have done the first addition, then the second mode is in preparation here, okay? Next clock tick. Now I have, for the very first mode, I have already the L plus M plus N that is already computed. So that's my second tick here, and then the third mode is already in preparation here. And then next clock tick, I have the cosine of this that has been done, and this element is already flowing to the next kernel. Okay, so that's really the way you have to think. You really to think in terms of streaming. How do you implement your algorithm in a streaming way? Okay, so the K appears in the second kernel. I have some data from the item that will come from memory here. Okay, they arrive at the chip, enter this kernel, and then now I will be able to, so on the next tick, the product will be done here with the first mode. Now, at this moment, we are done with this kernel. So this kernel has finished its work. All the data that has been produced are sitting here between the two kernels in some buffers that are automatically added by the software chain. So next clock tick, then I will have my first value of Q, and then I will be able to accumulate all these values. So while pathing all the different atoms, so now that's atom of the melt that are coming here, and I'm accumulating value here. Atom of the wall are now entering the FPGA. I'm accumulating here. Good, and then that's, so if I go one tick back, this is the last operation between K, my first mode, and that's the last atom that I have to consider. So next tick, then I change, so K, that's for the second mode that will start here while I finish this one. Next tick, I finish this one, and then at the next tick, then my first integral of Q value is ready and then flowing to the next kernel, while this kernel now continues the computation of integral of Q for the second mode. Okay, so now I have my first integral of Q here, and here I have only the atoms of the wall to consider, so only the green one. Okay, so I do the first multiplication that are here, and then I will aggregate the results inside my result here. And so here you have the concurrent execution of two kernels. Okay, you have here one kernel computing an integral of Q on one mode, while another kernel computes the CG port for another mode. And it goes on like this. Now this one is stalling because it's waiting for a new integral of Q. So I have to include, oh yes. And then it goes on until we have finished everything for all modes, for all atoms. Good. So the good thing, so with FPGA, now we can implement our own vector units, okay? As we are deciding of the hardware, now instead of treating one atoms at once at this part, we can treat them 3 by 3, okay? So it will put more pressure on the memory bus here, so to bring data here, but then I will be able to compute 3 by 3. So let's have a tick, then so 3 by 3, then I'm doing then 3 multiplication concurrently for the 3 first atom of the first mode. Okay, then I accumulate here, accumulate here, accumulate here. So now I'm starting to compute, to make the computation for the second mode, while I'm finishing to aggregate for the first mode. First mode is done now, flowing to the last kernel, while I can start with while this one is finishing for the second mode. Okay, and now we have the same pattern, 2 kernels executing concurrently at each tick mark, and then data is flowing here, and then we have with the integral of Q for the second mode that will enter the last kernel. Now we are finishing here the integral of Q for the last mode, while this one is already doing here. That's my last integral of Q. Okay, and I finish the last execution of the last kernel. and my CG pot is ready, has a good value inside the memory of the FPGA and can go back to memory here. All right, I hope it's you get the concept. So back to the algorithm. So for now, the current situation that we have implemented, so kernel for the conjugate gradient. This is working in the simulation environment, but we didn't perform yet the implementation on real hardware. That's the next step. We have a proxy application that is already working, so that called the kernels, but the kernels are executed in the simulator. The performance model tells us that it should be 3 to 5 times faster than B-socket hardware, so the execution of a single on a single FPGA. And yes, that we are really eager to measure so restitution time and energy on real hardware. So at the conclusion, on metal walls, so we have MPI plus OpenMP and MPI plus OpenACC version that are available, so that allows the code to run on a CPU, so on different kind of CPU and also on GPU architectures. So we managed to get an acceleration of 3.5 compared to the initial CPU version. And so yes, basically the code is ready for current architecture. We are deploying the new version, so for running on IREN, so as we speak. And for computing infrastructure, so definitely we will have still around for a couple of years multi-core CPU. So that's clear. Now, which one, that's not clear. We will see. So Intel, AMD, ARM. We will see what comes out. We will have definitely also heterogeneous system, so especially the tier 0 machine there that will try to reach exascale computing will very likely be heterogeneous. So CPU plus something else, so plus GPUs, so that's the open power line, and definitely they are on good track to reach exascale system. So we will see. But FPGA could be also another road to go there, and maybe yes, we have to keep an eye on this kind of device. Yes, good. Yep, and so one last word on a FET HPC project, so that's called Exa2 Pro. So that's a FET HPC project on programming productivity. The idea is to have the application on top that uses skeletons and component annotations. That is able to be translated into an intermediate representation, and then to do static optimization, technical debt management, performance analysis, some modeling on architecture and performance, some fault tolerance support, some memory management. So yes, a clever infrastructure here that generate the executable and then run on the hardware through a runtime system. Okay, so here with having as a target to be able to run on CPU, GPU, Xen and also the Maxeler DFE hardware. Okay, so that's the global picture. So Maison de la Simulation and myself, we are involved in this project, and with Metal World as a use case in order to evaluate the kind of solution that will be out, and especially so that the idea is to finish the Maxeler implementation and investigate mixed precision computation. So we will have a 2 years position for that, and another 2 years position to make a star PU implementation of Metal Worlds with investigating scheduling policy. Right, and I think that's it for this this webinar. So I hope you enjoyed. I could give you a flavor of what FPGA programming is, and if you have some questions, so I'm available to answer them. So how do we do for question? Yes, there is a question from François. Is it a question here?
No, it's not a question.
Ah.
Oh yes, it is actually.
No, question is what is a speaker contact? Okay, so my name is Mathieu Effelet. I'm working at Maison de la Simulation, and maybe I can give you my email if you want. Yes. Okay, that was one question. There is another question from Paolo. What about the programming language for FPGA? So yes, so I'm not an expert yet on FPGA programming. So for now, I only know the Maxeler software environment. And yes, that's true. I didn't show source code, but that's Java based. Okay, so you have some variable, so DFE var typically, that will be the stream, and then you make operation on them. To give you an idea, the kernel that we have written, in total, it's 400 lines, okay, to implement the conjugate gradient. So that's very similar to the amount of Fortran code that we have to implement. But yes, that's Java. That's completely different. So you have to start the implementation from scratch. I don't know if I answer your question. I hope. Good. So yes, so Paulo, I'm saying yes, that's good. So we have a question from Dirk. You mentioned mixed precision computation. Do you use double precision right now? I thought floats are costly in FPGA. Yes, the answer is yes. You're completely right. Computing, making floating point operation in double precision on FPGA is very expensive. Having fixed precision or simple precision, at least, you have a factor of 3. So typically, yes, you need 3 times less DSP to make single precision floating point operation compared to double. So you have really a factor of 3 here, not a factor of 2 like on a CPU, but even more if you know that you are not forced to use only either single precision or double precision like it's on CPU. You can decide the precision you want. You can say, okay, I want 17 bits for the mantissa and 3 bits for the exponent. That's completely possible in FPGA, and then you will use even less DSPs. But the thing is that there is a need of knowing which precision your algorithm are requiring, and this is not clear how you do that. But yes, definitely that's where FPGA computing could win even more than compared to CPUs. And the factor of 3 or 5 that I'm talking about, so with the performance model, is in double precision. So using the expensive double precision implementation on FPGA, we still get an acceleration of 3 to 5 on FPGA normally compared to CPU. So Dirk adds, and in your current test, fixed precisions or floats? No, as I said, so currently we're using all the model, and the implementation is using double precision, because yes, first I want to retrieve to find again the good results of the algorithm. We will investigate this mixed precision or lower precision algorithm afterwards in the second step. Any other question? No, doesn't look like. Good. Then I hope you enjoyed this webinar, and I hope it was informative. And then I leave the floor again to Nathalie, so that she can.
Thank you for your attention and for following this second webinar of ECO. The next one will take place the 11th of July, normally at the same time. You'll receive the news and the announcement soon. You have to know that this session has been recorded, so it will be available on the ECO website if you want to see it again. That's it. So thank you very much, and see you very soon. Thank you for participating. Bye.
Goodbye.